Hello, so we're going to start right here with y equals 2 to the x. An equation like this where the variable x is in the exponent is called an exponential equation. And I'm starting to wonder what an exponential equation might look like. So I want to get a graph. I want to get a sketch of this function. And when I'm not sure what a function looks like, I can go ahead and make one of these XY chart things where I've got x, 2 to the x, and y over here, and I can find some values for this sketch. I'm going to pick what I think are some important values, -3, -2, -1, 0, 1, 2, and 3, and then I'm going to go ahead and plug them in and see what I find. I'm going to start in the middle. I'm going to go with 2 to the 0. Anything to the 0 power is 1. Then I have 2 to the 1, which is just 2. 2 squared is 4. 2 cubed is 8. 2 to the -1 is a little more interesting. If you think back, 2 to the -1 is 1 over 2. A negative exponent changes the level. So it's 1 over 2 squared, which is 1/4. 2 to the -3 is 1 over 2 cubed, which is 1/8. So I'm going to graph the values that I have. So I have over 0 up 1, put a point there. Over 1 up 2, put a point there. I'm going to go over 2 up 4, put a point there. Then I'm going to go over 3 up 8. That's going to be a little bit off my screen, so I'll kind of estimate it as there. And then going backwards, going -1 puts me at 1/2. -2 puts me at 1/4. -3 puts me at 1/8. -4 would put me at 1/16. -5 would put me at 1 over 32. Negative puts me closer and closer and closer to that x-axis, but I'm never actually going to touch the x-axis. So that means running across my x-axis is a horizontal asymptote. I'm going to get really close to it, but I'm not going to touch it. And then drawing the graph through the points, you see a curve that starts off nice and low, but then flies up super high really fast. This is called an exponential curve. And the really important points on this exponential curve are the over 0 up 1, the over 1 up 2, and of course, again, that horizontal asymptote. Let's try this again real quick. Let's pick a different number. Let's go with y equals 3 to the x this time. If we put in a 0, 3 to the 0 is 1. We've got a point there. Put in a 1, 3 to the 1 is 3. We're going to have a point right here. 3 squared is going to be 9. It's going to fly real high, real fast. And then going to the left, 3 to the -1 is 1/3. 3 to the -2 is 1/9. So we're going to have that same horizontal asymptote running across, and it's going to fly real high, real fast. This is the exponential function, and again, you see those very important points of the over 0 up 1, over 1 up 3 with the horizontal asymptote. Both of these examples lead us to a new quick sketch. If we have y equals a to the x, our quick sketch is going to have a horizontal asymptote, then it's going to go over 0 up 1, put a point there, over 1 up a, whatever a is, and then whee, it flies away real high, real fast. All right. Now, in this quick sketch, we are assuming that a is positive. We're also assuming that a is greater than 1. If a is not positive or if a is not greater than 1, we will deal with that situation later. I'll show you how to do that in another video on another day. But for now, we're assuming that a is greater than 1. So any quick sketch I give you is going to look pretty much just like these. For example, y equals 7 to the x. Quick sketch it. Over 0 up 1, over 1 up 7. It's not to scale. Whee! And then don't forget your horizontal asymptote. Try for me, please. Quick sketch, y equals 10 to the x. Go, go, go. Over 0 up 1, over 1 up 10. Put a point there, whee! And don't forget your horizontal asymptote. Try one more time. Go ahead and quick sketch for me, please. Y equals 8 to the x. Go, go, go. Over 0 up 1, over 1 up 8. Whee! And there we go. That is the basic exponential quick sketch. Let's start again and let's see if we can get a really pretty version of y equals 2 to the x. So this is y equals 2 to the x, and I can see on my graph here these important points of over 0, up 1, over 1, up 2, over 2, up 4. Here's back 1, negative 1, up 1/2. Here's negative 2, up 1/4, and so on. I'm starting to wonder, just because I'm curious, what would the inverse of this function look like? I know that a function and its inverse are always symmetric around a certain axis. A function and its inverse are always symmetric around the y equals x axis. So I'm going to quickly draw one of those in there. This is the y equals x axis around which the function and its inverse will reflect. And so now to draw the inverse, what was x becomes y, what was y becomes x. So when I have 0, 1, the inverse will be over 1 up 0. When I have 1, 2, the inverse will be over 2 up 1. 2, 4 will give me over 4 up 2. Negative 1, 1/2 will give me 1/2, negative 1. Negative 2, 1/4, when I flip those around, will give me 1/4, negative 2. And with an inverse, everything that was horizontal becomes vertical. So the horizontal asymptote that you didn't see drawn in there before will now become a vertical asymptote for the inverse. And you'll see when you connect the dots, la 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 la, when you sketch in the inverse, you get a function that looks sort of like that. So I can see the inverse function, but I'm curious what that function actually is. So I'm going to start again with my y equals 2 to the x, and now I'm going to find the actual inverse function. So what was x becomes y, what was y becomes x. I have x equals 2 to the y, and I need to solve for y. But I can't simply cancel the bases out of both sides because the bases don't match. But what I can do instead is think of 2 as the ducky. And now the ducky ducks under, the log floats over. I end up with log base 2 of x equals y. And what we find is that the inverse of y equals 2 to the x is the function y equals log base 2 of x. And this is where we find a definition of a logarithm. A logarithm is the inverse of an exponential. And an exponential is just an inverse of a logarithm. Again, a logarithm is an inverse of an exponential. And we have found that this green function is the function y equals log base 2 of x. And you can see the mirroring of the two very important points where the exponential function is over 0 up 1, the log function is over 1 up 0, and the exponential function is over 1 up 2, the log function is over 2 up 1. And finally, where the exponential has a horizontal asymptote, the logarithmic function will have a vertical asymptote, which leads us to another new quick sketch. The quick sketch of log base 2 of x looks just like this. Vertical asymptote, ta, 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 ta. And then it's over 1. It's always over 1. And then it's over whatever the base is, so in this case 2, up 1. Put a point there, and then it comes flying up and away. So let's take a look at the quick sketch for y equals log base 5 of x. So we're going to have a vertical asymptote. It's going to be over 1 up 0, over 5 up 1. Put a point there. Whee! Big dots fix everything. There we go. Let's go again. Try for me, please. Quick sketch. Y equals log base 3 of x. We're going to be over 1 because it's always over 1. Then it's over 3, up 1. Put a point there. Vertical asymptote. Ta, 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 ta. And whee! Try one more for me, please. Quick sketch. Y equals log x. And you might think, but Miss May, you didn't tell us what the base is. Ooh, but this is the common log, remember. And what is the base on a common log always? It's y equals log base 10 of x. So now I can quick sketch that over 1 over 10 up 1, vertical asymptote, ta, 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 and jump and fly away. There we go. So now I want to take a look at a nice basic y equals log base a of x quick sketch. And I need to think some things through. I know I have my vertical asymptote. I know it's always over 1. Then it's going to be over a, whatever a is, up 1, put a point there, and whee, there we go. Here's my quick sketch, and here's where I need to think some things through. Looking first at all of my x values. Notice that all of my x values are greater than 0. They don't equal 0. They're not less than 0. All of my x values are greater than 0. So now I need to think a little bit deeper. And to do that, I'm going to turn my logarithmic function back into an exponential function. So I'm going to write it with the log on the left. And now I'm going to have my ducky duck under, the log floats away, and I get x equals a to the y. Notice that this exponential function here is actually the same as this logarithmic function here. It's just a different way of writing the same problem. And people say, well, isn't a log an inverse of an exponential? Yes, it is, except I haven't switched the variables. So these two functions here are equivalent functions. It's only when I switch the variables in the inverse process do I actually get the inverse. So one function is written in logarithmic notation, one function is written in exponential notation. And the question I have for myself is, can a equal 0? It's a good question. If a was 0, I would have a to the y equals x. So that means if y was 1, x would equal 0. If y was 2, x would equal 0. If y was 3, x would equal 0. But we just talked about how x has to be greater than 0. So can a equal 0? No, a cannot equal 0. All right, we have a different question now, and that is, can a be negative? So let's pick a negative number. Let's take a number like -2. Could a be -2? Looking again at the exponential version, we would have x equals -2 to the y. So if y equaled 1, x would be -2. But like we mentioned just a moment ago, x has to be greater than 0. So can a be negative? No, a cannot be negative. So if a can't be negative, and if a can't be 0, that means that a must always be greater than 0. That's super important. So now the last thing that I'm wondering about is, can a equal 1? If it did, again, using the exponential version of our function, we would have x equals 1 to the y. Let's pick some values for y. If y was 1, x would be 1. If y was 2, x would still be 1. If y was 3, x would still be 1, and so on. If we looked at that, we would have over 1 up 1, over 1 up 2, over 1 up 3, and our sketch would look just like that, like a vertical line, which is not a function, and so therefore it's not a logarithmic function. Can a equal 1? No, a cannot equal 1. So our three very important things to remember is that a cannot equal 1, a has to be greater than 0, and x has to be greater than 0. And the way that I remember that easily is that for any exponential function, y equals log base a of x, both of these spots, the a spot and the x spot, both of these spots have to be greater than 0. That covers our x is greater than 0 and our a is greater than 0. Both of those spots are greater than 0. And then this little guy, the a, cannot equal 1. Again, y equals log base a of x. I just go, both of those are greater than 0. This little guy cannot equal 1. Try it. Y equals log base a of x. Both of these are greater than 0. This little guy cannot equal 1. Say it. Y equals log base a of x. Both of these are greater than 0. This little guy cannot equal 1. So now let's get fancy solving some functions. If I have log base 3 of 4x minus 7 equals 2, and I've been asked to solve for x, I can convert to exponential notation. The ducky ducks under, the log floats away. I get 4x minus 7 equals 3 squared. That means 4x minus 7 equals 9. Add the 7, I get 4x equals 16. Divide by 4, I get x equals 4. And I should be done, except I now know that both of these spots have to be greater than 0, and this little guy cannot equal 1. We always have to check our logs at the end to make sure we satisfy these conditions. Now looking at the base on the log, 3 is greater than 0, 3 doesn't equal 1, 3 is just fine, 3 is not a problem. And I need to check this 4x minus 7. When I plug in my value for x, I need to check that this is greater than 0. Plugging in the 4, I do get a value that's greater than 0, therefore my answer of x equals 4 works, and it's totally fine. Try this one. Log base x of 64 equals 2. The little ducky ducks under, the log floats away. I get 64 equals x squared. I'm going to bring in my own square root, and when I do, I don't forget my plus or minus, so I get x equals plus or minus 8, and I want to be done right there, except both of these have to be greater than 0, and this little guy cannot equal 1. 64 is greater than 0, but the x is a concern. If I plug in positive 8, positive 8 is greater than 0, positive 8 does not equal 1, positive 8 works just fine. If I plug in negative 8, negative 8 is not greater than 0. Therefore, negative 8 gets disregarded. My only answer is x equals positive 8. If you forgot to do the plus or minus on the radical, you got lucky in that problem. Try this one. Log base 4 of x squared minus x minus 8 equals 1. The little ducky ducks under, the log floats away. I get x squared minus x minus 8 equals 4 to the first power. That gives me x squared minus x minus 8 equals 4. Subtracting 4, I get x squared minus x minus 12 equals 0. Factoring gives me x minus 4 times x plus 3. And I end up with x equals 4 and negative 3. Maybe they both work. Maybe neither of them work. Maybe only one works. I can only know by checking, and I know that both of these spots, both of those locations, have to be greater than 0, and this little guy cannot equal 1. 4 is greater than 0, 4 doesn't equal 1. This spot, the base, is perfectly fine. It's this that is now my concern. That whole term has to be greater than 0 when we plug in the answer possibilities. So plugging in 4, I get 16 minus 4 minus 8. I don't even have to actually do that math. I just need to know that it is greater than 0, which it is, so 4 works. Plugging in negative 3, I get 9 minus negative 3 minus 8. That's going to be 12 minus 8. And again, that works. It's greater than 0. Negative 3 works also, so I get 4 and negative 3 is my answers. Sometimes students automatically disregard negative answers, but that's not always the case. What determines it is the math within the problem, not just the negative sign on the answer. All right, let's go with one final problem. Give it a try and see what you come up with. Let's go with log base x of 2x plus 5 equals 2. The little ducky ducks under, the log floats away. I get 2x plus 5 equals x squared. Subtracting the 2x and the 5, I get 0 equals x squared minus 2x minus 5. I can try to factor it, but it's not going to factor. So I'm going to switch to the quadratic formula. I get x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. That gives me 2 plus or minus the square root of 24 over 2. That's going to be 2 plus or minus 24 is 4 times 6. 4 is 2 times 2. 6 is 2 times 3. So you see that we have the 2 rad 6 over 2. And finally, we can factor out the 2, which gives us 1 plus or minus rad 6 over 2. The 2's cancel. We end up with x equals 1 plus or minus rad 6. And I just want to throw a box around it and walk away, but I can't yet because I know both of these have to be greater than 0, and this little guy cannot equal 1. So let's start with 1 plus rad 6. Rad 6 is somewhere between rad 4 and rad 9. Rad 4 is 2, rad 9 is 3. So we'll call it maybe like 2.5. So 1 plus rad 6 is maybe like 3.5. So if I plugged in approximately 3.5 to this log, 3.5 is bigger than 0. 3.5 doesn't equal 1. 3.5 times 2 plus 5 is definitely bigger than 0. The positive version works. If I go 1 minus rad 6, again calling rad 6 2.5, 1 minus 2.5 is negative 1.5. So plugging it into the base, I have negative 1.5 is not greater than 0. I have to disregard the negative answer, and the only answer I get is x equals 1 plus rad 6. All right, guys, thanks for watching.